If you remember, we are interested in finding the pulse transfer function, and this is the C in the Z domain over the E in the Z domain. To do this, we are interested in finding first the C star of S over the E star of S. The reason for this is we discussed we can use a residue method to go from, for example, C in S domain, we can go into the C star using the residue method, and then we can go to the Z domain by replacing the relation of Z domain and the S domain. So using the residue, we can go to the C star, and then from the C star we can go to the Z domain. That's one method. So in order to find this ratio, let's write out the relation between the output and the input. Now from this open loop system, we know that C of S equals to H of S multiplied by E star of S. Now if we star both sides, we know we can get the C star of S equal to H star of S E star of S. So the pulse transfer function can be written as such. Then we can get H in the Z domain once we do the substitution. Remember that the H of S is a continuous time domain and the input is discrete. Therefore, inside H of S, it should include the zero order hold. So H of S in fact look like this. That's the zero order hold transfer function, which is included inside H of S, so that we can go from a discrete format to a continuous time format. And perhaps the planned transfer function, we call it G of S. And if you notice that from Laplace transform, the exponential of negative st is a delay factor. So the zero order hold always introduce a delay to the planned transfer function. And for convenience, we can move the denominator of the zero order hold to the denominator of the planned transfer function. In this case, we can express the zero order hold as 1 minus z to power minus 1. Remember, in general, we do not show the data hold transfer function separately, but we always combine it with the transfer function of the part that follows the data hold. In our case, H of Z is what we call the pulse transfer function. And this is the transfer function between the sampled input and the output at a given sampling instance. And remember, the pulse transfer function will only exist if the input is sampled before it's being applied to the continuous time part. For example, if you have an input which is applied to an analog part before it's being sampled, then in this case no pulse transfer function can be obtained. And this is also true in some cases where you have E of S is fed into somewhere else in the loop. without being sampled, this also leads to no pulse transfer function. However, you can always still obtain a relation between the output and the input.
Now, every time we refer to the word system, we mean it's a linear system where superposition holds, and also it's time invariant as well, where the coefficients are constant and not varying with respect to time. C of S equals to G2 of S multiplied by A star of S. This is one equation. The second equation is A of S equals to G1 of S multiplied by E star of S. Ultimately, we would like to find the relation between the C star of S and E star of S. To do this, if you notice in equation number 1 that the A star of S has the information in terms of E star of S and G1 of S. So our objective here is to substitute the equivalent value of A star of S. To find A star of S, we will apply the starred Laplace formula on equation number 2. This leads to, so the star of A of S will be A star of S equals the star of G1 of S multiplied by E star of S. This will lead into G1 star of S E star of S. So all what we need to do now is to replace the value of A star of S in equation number 1. We end up with C of S equals G2 of S multiplied by G1 star multiplied by the E star of S. Remember, we would like ultimately to find the C star of S in order to find this relation. So if we apply the starred Laplace formula again on C of S, we get C star equal to G2 star equal to G1 star of S and E star of S. Now substituting the relation Z equals to E ST, or S equals to 1 over the period ln Z, in this case we can get the equivalent Z transform of the above. Now we can express the output clearly in terms of the input E of Z, and the answer will be G2 multiplied by G1 on the Z domain. If we consider this sample data open loop block diagram, we notice that it comprises only of one sampler and two blocks in the continuous domain. In this case, we can express C over S as equals to G2 over S, G1 over S, multiplied by the E star of S. And E star of S is just after the sampler. As we discussed in the previous example, our main objective is to find C star of S as a function of E star of S. This will allow us to go to the Z domain. To do this, we can apply the starred formula. So starting the whole function, we get C star of S equals, now because we have two functions multiplied in the Laplace domain, the star of both occurs after the product. Be careful. So this item here is not equal to G2 star of S, G1 star of S. So this is wrong. Okay? Let's get back. So the star of E star of S will be the same, E star of S. And in this case, we can find the relation in the Z domain and the open loop transfer function can be obtained as C of Z over the input equals to the G1, G2, both multiplied before converting this to the Z domain. Let's consider this example. The sample data open loop block system comprises of only one sampler. But what's interesting in this example is the input is applied to the analog element G1S before both being sampled. Now the information of the input E of S is now blended after it has been multiplied by G1 of S before the sampling occurs. In general, no transfer function can be written. This is true when the input E of S is applied to an analog element G1 of S before they are being sampled. However, we can always express the output C of S as a function of the input, as a function of the input. Now remember that the input here, in this case, is not E of S alone, it is the product of E of S and G1 of S. Now if we apply the technique developed in the previous chapter, we can express now C of S equal to G2 of S multiplied by the A star of S. And we know that A of S is equal to G1 of S multiplied by E of S. For us to find the information in A star of S, if we apply the star Laplace formula, what we get is a star of s equals, since these two are intercontinuous domain, the starring of the product will lead to G1 E then over bar star of s. Now substituting that information up in equation number 1, we get C of s, equals to G2 of s multiplied by G1 E of s. Again, we are interested in the C star of s to find that relation between the output and the input. And as we already mentioned, and we know that there's no transfer function that we can write for this specific sample data open loop system. However, we said that we can express always the output in terms of the input. In this case, this is the output and this is the input. So applying the starred Laplace formula again, what we find is C star of s equals to G star of s, and this one remains as is. This becomes C of z equals to G2 of z multiplied by G1 E the z domain. We have covered this similar example before, so if we apply the same technique over again, we can find that the C of s equals to the plant transfer function multiplied by the zero order hold equivalent multiplied by the digital controller, the Z domain, multiplied by the input. Now the input E star of s is just after the sampler. If we combine these two and we call it G of s, then applying the starred formula, we get C star of s equals to G star of s, D of z stays as is, and we get the E star of s, and that input as well stays as is. And we can easily convert this to the Z domain, so we can end up with the output, the Z domain, equal to G, the Z domain multiplied by the computer transfer function and the Z domain multiplied by the input and the Z domain. And if you recall, the G and the Z domain is actually equals to the Z transform of the multiplication, which we've done already before in the previous chapters. So the transfer function here exists, and the output can be expressed in terms of the input E of z. And by this we have reviewed briefly 4 different types of sample data open loop systems. And you have to be careful how to apply the start formula. This will be used later in the closed loop systems as well.